When you rotate it the other direction, the ball does come out. So you can see this here.
We're here at the FTC World Championships for the DECODE season, getting an up-and-close look at how different robots function.
We have a vertical spindexer.
Today we're taking a look at 21430 BroomBots.
Here's all of our iterations.
Wow! The whole purpose of FTC Robots Revealed is to get an up-and-close, personal look at how do different mechanisms on robots function.
So we just have this 3D printed latch here.
Now, BroomBots have a really slick vertical indexer with some passive ejector to be able to have a high throughput for the artifacts.
It is coated in duct tape to prevent ESD.
They've got an underhanded hood and a whole bunch of really interesting electronic tweaks to take a look at.
Tell me about your general robot. What's your overall strategy for this season? What's your robot composed of?
This is our robot. We named it Sisyphus. And this year our strategy, the game, includes taking this artifact and moving it through our robot into the spindexer. So this is our intake right here. It moves up and down. And we have vectored intake wheels that move the artifact into the middle.
It has mechanism wheels because we wanted to be able to funnel artifacts into the spindexer, like that, as well as funnels to help with that as well on the sides. The cover is to help us open the gate on the ramp. The middle wheels these ones are gecko wheels that we cut the rim off of for maximum texture and grippiness. And we've got these wheels here as well. And then our mechanism wheels have grippy tubing over the rollers because we noticed that often in autonomous especially, it would run into the rows of artifacts and then they would bounce away from the slippier original rollers they had. So the texture has both helped with that and increased speed greatly. The side plates were custom cut with a bandsaw and drill press that allow it to move up and down, inspired by some FRC robots we've seen, and it kind of pins the artifacts into the spindexer better.
Once it is inside the robot, we have a vertical spindexer, the vertical spindexer, which moves the artifact around the central axis and gets it to the outtake. And we have a passive ejector on this spindexer, meaning when you rotate it one direction, nothing happens, and when you rotate it the other direction, the ball does come out. So you can see this here.
Sorry, I totally missed the action of that. Can you try that one more time? It was this one right here, yes?
So here's the ball going one direction.
So you rotate one way and it can push the out of the way, and then you rotate the other direction, and that's when it gets up and into your flywheel.
Yep, and then this is our outtake. It is an underhand hood that can change the angle, and it has a flywheel which is reinforced with steel flywheels for rotational inertia.
Very cool. Why did you guys decide to go with an underhand scoop?
So we utilized the underhand hood for size constraints first because it worked really well with integration with the vertical spindexer. We could just rely on gravity a lot to get the artifacts out of the spindexer, and then also because we like having the top spin on our artifacts because of the Magnus effect. There's a downward force because of how the artifacts are spinning, so they go into the spindex or into the goals a lot more consistently. Yeah.
And that's with this little servo here is the one that controls the lift of that hood coming out?
This one down here.
Oh, this one down. Oh, okay.
Yeah, we have a little rack and pinion down here.
Oh, easy.
Yeah.
Nice and simple. And then your spindexer, you kind of just totally glossed. So how does that actually function? And how do you know when a ball is in there? How do you know when it's time to rotate around and so on?
Yeah, so we have a super speed swift servo, and then we have this three-pronged paddle, and we went through a bunch of iterations of paddles. I think we have a board over here with them. But basically, they just have this cutout here. The artifact will come in, and then we have 2 color sensors, so we know what color, and we can sort our artifacts. And then we also have a little flap with 2 limit switches behind it, so we know when an artifact is in the spindexer.
Yeah, you can totally hear that click as you come on in there, right?
Here's all of our iterations.
Wow, okay.
So we started here with our basic flat shape, and then we added curves so that we could support the ball. And then we also, after this, we made it bidirectional so that we could go both directions And then this last one has cutouts for our passive ejector.
Wow, I love seeing that, and that's
Absolutely.
I love seeing iteration on designs as well. Super, super slick. And then, question for you on that dual color sensor intake down below. Dual color sensors because you found that one wasn't reliably picking up with the holes in the wiffle ball?
It was for redundancy, yeah. We were concerned, it was a risk mitigation strategy because we were concerned we wouldn't be able to get a good reading if the artifact was over a hole on the color sensor. So for redundancy's sake, we have that. We have redundant sensors for almost everything. We have 2 limit switches. The spindexer, 2 limit switches for our lift. Yeah.
Just to make sure that things are running, and you just have an OR gate when you're running things then, yes?
Yes, exactly.
Cool. And then you guys also have a cool little hatch at the back. Can we open up the hatch and take a look at the inside there?
Sure thing. So we just have this 3D printed latch here, and then inside we have our little battery drawer. It just keeps our battery from falling out. We can hold the new Go Build batteries as well as the old ones in here.
And on the back end, you've got your limit switches down here that you were saying before.
Yeah, so these are the lift limit switches for our little plate, and then these limit switches are for our spindexer.
Okay, and then you just wired those up yourself just with a standard stock limit switch like you'd see on a 3D printer or something like that, right? Like a laser cutter.
Uh-huh.
And then you said lift. Let's talk about your lift.
So here are our lifts. The cool thing about them is they are 55% 3D printed. The printed parts are made out of PETG carbon fiber. We went through multiple different material testings with a load cell, to land on carbon fiber PETG. It's rigged in a continuous fashion, so the belt goes all the way through the entire thing. We have an elastic band on the top here, so we don't kill our motor and break everything if we go up too far.
Oh, that's this one right here. That's your, okay, yep.
We did multiple stress simulations to ensure that this design was strong enough, and we have found through those stress simulations that it is twice its needed strength.
And here's the material testing.
Ah, okay. And PLA, like glass fiber infused.
We just went kind of basic PLAs, so this is PLA tough, this is PLA carbon fiber, this is regular PLA, and then this is just regular PETG.
And then obviously your PETG with carbon fiber is what ended up winning in the end. Awesome. Super, super cool. And then what are you driving this with? What's your gear ratio for your main?
I believe our gear ratio is 5:3:3 onto there.
So it's a 1 to 45? Making you do quick math on the spot. Yeah. Totally feel you there. Totally feel you.
So, and then on the front we have our ratchet mechanism that we use to stay lifted.
Where is your ratchet mechanism? That's tough to see.
It's really tucked in there.
Oh, okay, I see it there. Yeah, it's that little
really
black plastic gear right there with that, and that's just so that you can passively not fall down and crush into the robot.
Exactly. Yeah.
Can we take a look at the belly pan? Is that okay? Because you said you had a plate that this thing runs on top of. Yes.
So this is our custom plate that we got water cut. It is coated in duct tape to prevent ESD.
Okay.
We ran into that once at a competition, and we did not want that to happen again. So.
And you said ESD. I noticed you guys have a whole whackload of different ESD event things. You've got ferrite chokes on motor runs. You've got hot glue, or hot snot, as an old mentor of mine called it, just about everywhere. What kind of stuff have you guys done to sort of mitigate ESD events?
One of the biggest things that we just did recently was we made these covers over our intake to open the gate, and so these were made out of aluminum.
Yes.
And so one of our things we thought about were like, this is a big ESD issue if we're running around with this on the front of our robot. And so we covered these with multiple layers of tape. We have vinyl wrap on the bottom, and then it was getting very much torn up in practice. So we added some grippier, thicker stuff that is also currently getting torn up. But that was one big thing to eliminate ESD.
And then it looks like you've also got like polycarbonate shielding around the rest of your robot as well.
Yes, we do have polycarbonate shielding. There's no metal on the very outside of our robot. We have grounding straps in here as well, connecting all of the different subsystems.
And then what kind of things do you do on the driver automation side to make your life a little easier as a driver?
We have driver automation basically everywhere. So our entire intake system is automated, our entire spindexer system is automated, and our entire launcher system is also automated. So with a single push of a button, we have the intake sequence go off.
Yep.
These balls enter the spindexer. They're automatically categorized when they hit the limit switch in the color sensor. They are automatically categorized and sorted into this. And then when we are ready to fire, it automatically shoots them all in the correct order. And we have the vision camera up here, which auto-calculates the distance, and so that sends to this, and it does the correct hood angle and the correct RPM for the flywheel.
And what are you guys most proud of on your robot?
I would say our passive ejector. We had a big kind of like redo after state where we sat down and we looked at our goals and we decided that, thank you so much, we decided that our ejector was not working as fast and efficiently as we had hoped, especially at the beginning of the season. So here's iteration 1 of our ejector, and you can see that it would take 3 motions to eject 3 artifacts. And with the passive ejector, it only takes 1, and we can do it in 0.6 seconds. So this was a massive upgrade from our previous ejector, and we managed to do it in a couple months between state and worlds, and it has increased our performance quite a bit. So it is right in here. You can see it right there.
Yep.
It is held on with surgical tubing, which is clipped right into
Right back
with
up
some
there.
zip ties. We tighten it once in a while if need be. And so it's been working very, very well. So we are very proud of that.
Very cool. Awesome. Well, thank you so much for being able to share off your robot, guys.
Thank you so much.
Thanks.